Hi everyone! In this video, we're going to talk about systems of linear equations in three variables. So previously, we had talked about systems of linear equations with two variables, and we worked with them in the form that is shown here. So ax plus by equals c. And when we found the solution, we had an ordered pair. We had the x value and the y value. But now, when we're working in three variables, we are throwing in a third variable of z. And it's going to have a very similar form, except now we have three terms that equal a constant. So we're going to have ax plus by plus cz equals d. Now, when we are graphing these three variable linear equations, we're now no longer two-dimensional, but we're three-dimensional objects. So here I have pictures of what equations of this form look like in three-dimensional space. So if we have one of these equations, we're going to get a plane that looks like this. And let me go ahead and show you in GeoGebra. So now, if I look at it from this view, it looks like, oh, that's just a line. But if we rotate it, we see the plane. If we have two three variable linear equations in our system, this is what we get, a second plane. And remember that when we were solving our two variable linear systems, we wanted to see where our lines intersected. And that was our solution. Well, now we're looking at where do our planes intersect. And if you look here, you see that it's a line in which they intersect at. So that means we're going to have infinitely many solutions. Our solutions are going to be on that line. And then our third possibility is if we have three variable linear equations in our system. And remember, if we're looking where do all these planes intersect, well, this time it's going to be at one singular point. And so in this case, we would only get one solution. So let's go back to our resource. One thing that I want to talk about is we had for our solutions of our two variable system were ordered pairs. But now since we have that extra variable of z, we're looking for an ordered triple. So it's going to be of this form, and it's going to include x, y, and z. And it's just like alphabetical order. So the x comes first, y is the second coordinate, and z is our last coordinate. We are going to solve our system of linear equations in three variables using the elimination method. And so here are the 5 steps that we're going to use every time we tackle one of these problems. And it's very similar to what we talked about previously with our two variable linear systems, except this time we have a few more steps because we have one more variable as well as more elimination that needs to be done. So step 1, essentially what you're doing is you're going to take any two pairings, so two sets of two equations from our original system, and you're going to eliminate the same variable. So let's say I take the first and second equation and I eliminate x. Well, then if I take the second and third equation, I also need to eliminate x. So make sure whatever pairing you're picking, you're always eliminating the same variable, whether that be x from both, y from both, or z from both. It doesn't matter which variable you choose to eliminate first, as long as you're choosing the same variable. And the second step, after step 1, you're going to end up getting a linear system in two variables with two equations. And so now you're going to you can choose the addition or the substitution method to then eliminate one of those variables. So in my example that I talked about, if we now have an equation with y and z, I can eliminate y and get a value for z, or I can eliminate z and get a value for y. Step 3, now that you have that value, you're going to back substitute it into one of your equations from the previous step. to get the value of our second variable. Step 4, now that you have the value of 2 of your variables, you're going to go back to your original system, pick any one of those equations, substitute those values in that you found for step 2 and step 3 for those variables, and you're going to find our last variable. And then step 5, you're going to check your solution in all of the original equations. Let's go ahead and see an example of this. So here we're solving this system with 3 equations. We have equation 1 is x minus y plus 3z equals 8. Equation 2 is 3x plus y minus 2z equals negative 2. And then equation 3 is 2x plus 4y plus z equals 0. So referring back to those steps that I had in the previous table, we are going to go ahead and reduce our system to 2 equations in 2 variables. And so remember, it doesn't matter which equations you choose or which variables you choose to eliminate here, as long as it's the same variable. So I'm going to go ahead and eliminate x. And my first pairing of equations is I'm going to use equation 1 and equation 2. So we have x minus y plus 3z equals 8 and 3x plus y minus 2z equals negative 2. Now remember, if I am using the elimination method, I need to have it so that if I'm eliminating x, when I add these 2 equations together, my sum of my x terms is 0. So then we're just left with y and z. So in order to do that, I need to have something x plus 3x equals 0. And we want this to be a negative 3x. So I'm going to multiply this whole equation by a negative 3. So we end up getting the new equation, negative 3x, and then negative y times negative 3 is a positive 3y minus 9z equals 8 times negative 3 is going to be a negative 24. Our second equation, we don't need to change it in any way, so I'm just going to rewrite that under our new equation for equation 1. And then we add. Well, negative 3x plus 3x, we get 0 x's, so those did eliminate. Then we have 3y plus 1y is 4y. Negative 9z plus a negative 2z is negative 11z. And negative 24 plus negative 2 is negative 26. So now we have an equation in 2 variables, and we have gotten rid of x. Now I'm going to do the same thing, eliminating x, but I'm going to choose to do it with equation 1 and 3. Since we've already used 1 and 2, you can use any other combination you want. You could do 1 and 3, you could do 2 and 3, just as long as it is not 1 and 2 again. But like I said, I'm going to use equation 1 and 3. So we have x minus y plus 3z equals 8 for equation 1. And then equation 3, we had 2x plus 4y plus z equals 0. Now, remember we're trying to eliminate x, so when we add these 2 equations together, we need to get 0 x's. So what I'm going to do is multiply this first equation by a negative 2. Because then we'll have negative 2x, and when we add that with positive 2x, we cancel those out. So go ahead and continue distributing this negative 2 to our entire equation for equation 1. So we get a positive 2y, negative 6z, and 8 times negative 2 is negative 16. All right, and then no change to our third equation. We're just going to go ahead and rewrite that underneath here. And we add. So we end up having negative 2x plus 2x is 0x. 2y plus 4y, we have 6y. Negative 6z plus z, we have negative 5z. And negative 16 plus 0 is negative 16. So we now have a new system, which I'm going to write here in step 2. Choose to do this in a different color. So we have 4y minus 11z equals negative 26. And we had 6y minus 5z equals negative 16. And before you continue to step 2, I just want to remind you, make sure that the two equations you got from step 1 have the same two variables. So we have a y and a z in both of these. No x's, which is what we wanted. All right, so now we're going to solve our new system. And this is just like we've done previously in the videos beforehand. And I'm just going to choose to eliminate y. You could eliminate z here if you like. It's whatever you prefer. Either way, you're going to get the same answer. So if I'm going to eliminate y, again, when I add these two equations together, I need to get a sum of 0y. And so to do that, I'm going to find the least common multiple for 4 and 6. And that's actually going to end up being 12. And so to do that, I multiply 4y by a negative 3, just because I want it to cancel out when we add. And then I need to multiply 6y by positive 2, and then I'll get what I need to eliminate y. So multiplying this whole first equation by negative 3, we have negative 12y plus 33z equals a positive 78. And then here, multiplying our second equation all by 2, we have positive 12y minus 10z equals negative 32. And we're adding these equations together. Negative 12y plus 12y, we get 0 y's. 33z minus 10z is 23z. And then 78 plus negative 32 is going to be a positive 46. We're not quite done yet. Yes, we eliminated y successfully, but we need to solve for z. And we can here. We have 23 times z, so we're going to divide both sides by 23. And when we do, we end up getting 1z equals 46 divided by 23 is 2. So we have now found our value for z. Now we can move on to step 3. And now that we have the value of z, we can go back to what we found in step 1 in those equations, and we can plug in our value for z into any one of these equations. The 4y minus 11z equals negative 26, or the 6y minus 5z equals negative 16, and we can find the value of y. So I'm going to go ahead and I'm just going to use the fifth equation, which I'll call this second one here. So we're going to use 6y minus 5z equals negative 16. I now know that z equals 2, so I can substitute in the value 2 for z. And now we solve. So I have a negative 5 times positive 2, so we get negative 10 there. Rewrite the rest of my equation. This 6y is being subtracted by 10. In order to get y all by itself, I need to add 10 to both sides. And when we do, we get 6y equals, right, the negative 10 and positive 10 cancel, and we get negative 6. 6 times y, to get rid of that 6, we have to divide by 6 on both sides. And we end up getting y equals negative 6 divided by 6 is negative 1. Now we have to find our x value. We have y and z. So to find x, we're going to pick any one of these equations from our original system and plug in our values for y and z, and then solve our equation for x. I'm going to choose to use equation 1. You could use either of these, 1, 2, or 3, but I'm just choosing 1 because x is already isolated. And by that I mean it's not being multiplied or divided by anything. We only have addition and subtraction with that equation. So using equation 1, let me rewrite that really quickly. So we have x minus y plus 3z equals 8. Substituting in my values for y and z respectively, we have a negative 1 for y and a positive 2 for z. All right, now we can do some of this multiplication. So we have a minus negative 1, or you could read this as negative 1 times negative 1, which is going to be a positive 1. And we have plus 3 times 2, which is positive 6. And we still have this x out in front and equaling 8. We can do this addition. So we have 1 plus 6 is 7. And then lastly, in order to get x by itself, we need to subtract 7 from both sides. And when we do, we get x equals 8 minus 7 is 1. So right now our proposed solution, I'm just going to label this solution, is the ordered triple. Our x coordinate is 1, y coordinate is negative 1, and our z coordinate is 2. But remember, we have that additional step, step 5, and that's to check our solution in our original system. So we have to check it for equation 1, 2, and 3. So there's kind of 3 parts to this step 5. I'm going to check it in equation 1, and I encourage you to do the same for equations 2 and 3. So equation 1, we had x minus y plus 3z equals 8. When we're checking a solution, remember that we substitute in our proposed values for x, y, and z, but I am not going to manipulate the right-hand side at all. We're just checking, does this in fact equal 8? So let's substitute in our values. So we have x is 1, y is a negative 1, and z is 2. Simplify our left-hand side. So we have a negative 1 times a negative 1, which is a positive 1. And we have a 3 times 2, which is a positive 6. Doing our addition, we have 1 plus 1 is 2. 2 plus 6 is 8, which this is in fact true. And then remember, you have to do the same thing for equations 2 and equations 3. And when you do that, you will find that this solution does in fact work. And so remember, if we have one solution, that means our 3 planes are intersecting at one singular point. So solving systems of linear equations with 3 variables is very similar to the process of solving systems with only 2 variables. But the main difference is that our answer is now an ordered triple, so we have an x, y, and z instead of just x and y coordinates. And we had to apply the addition method twice in order to eliminate 2 variables instead of 1. I hope you find this video helpful and wish you luck as you're solving your linear systems in 3 variables.